So very good afternoon to all of you, and I really extend my thanks to the organizer, Professor Srinivas, and others here, my student, my PhD student Vandita, and all for coordinating and giving this opportunity to interact with you. I had always I was thinking that sometime I should come to IIT Dhanbad. In fact, from my college time itself, I was having a plan that I should visit, because this is a very reputed institute. As IIT, it may be very recent, but otherwise, it is completing its 100 years. So that way, thank you very much for giving me this opportunity, and I was asked to talk about this particular topic, that fundamentals of GPS and its application in water resources. Okay, so I'll be concentrating mostly on some of this topic. Well, so shall I come here, or I should talk? What is the policy you follow? I don't know, but generally I am not that comfortable when I am sitting. Okay, okay, fine. Well, now this, if you see that on this, I will start from very fundamental. Maybe I do not know the composition. Some of you may be doing a lot of advanced studies in geoinformatics. Some of you may be coming from a different background, and that way, considering that, I thought that I will start from very basics, and that way, please excuse me if it becomes very, very basic for some of you. Okay? Well,
sir, it will work on that slide. It will work on projector on it, sir. That is TV screen.
Okay, if I say that this rhino is at this much distance, one is supposed to baby rhino and the main rhino or the mother rhino, it is at this much distance, is it sufficient to indicate position of the baby rhino? I mean, definitely we all know that it is not sufficient, because if I say just that this distance, then we can take a circle and at any point this rhino can be. Okay, so that way this is not sufficient. Now if I say that, okay, it is at this much distance from that tree, is it sufficient that we can locate that where that rhino, baby rhino is? Is it sufficient? It's sufficient? How many of you are for sufficiency? Or how many of you are not for the sufficiency? For sufficiency? Not for sufficiency, okay. So now, see, at the same distance, from here to here and from here to here, there can be another position on this side where this rhino can be. If I measure the same distance from here to here and here to here, I can get another position. So this is also not sufficient. That's why in survey, in very basic survey of civil engineering, we always talk about 3 points to be located for fixing a particular point. So we need to have another point like this. Suppose here I am putting a pillar, making a permanent, and we are saying that this is sufficient. Is this sufficient? Now how many of you will go for considering this as sufficient? And how many of you will go for that this is not sufficient? Not sufficient, how many are there now? Or is it sufficient that this rhino position is fixed?
Not sufficient.
Not sufficient. Why?
It will require the coordinates of the pillar.
Coordinate of this pillar, if I consider as fixed, suppose coordinate of this pillar if I consider as fixed, then is it sufficient?
No, sir.
Still no. Why?
Sir, one of the benchmark is moving.
One of the benchmark is moving means this is also moving. There are several issues that, well, this is there, but again on a vertical plane, but on a horizontal plane it is otherwise sufficient, but this can be moving. So its location at every time will have to be very sure that what is its location. So now coming from this very fundamental, I'll go to another situation like this is not visible, but there is a small house. There is a small house located in this point. Now if I want to find what is the location of this house, now this is, I am coming to a 3D plan. Okay. Earlier it was on a horizontal plane, it is okay, but then it is now in a 3D plan. Now, say this bird to this particular location and two birds all are moving. All are moving. This bird is also moving, this is also moving, this is also moving. Okay? Whether this is moving or relatively moving, it's a different point. Now if I say that this is the distance from this bird to this one, so how I can measure the distance? That is again another issue. Well, next, suppose if I say that this is the distance from this bird and say this is the distance from this sun. Is it sufficient again? Is it sufficient? No. Why? These are moving. If I consider that these positions are known, then is it sufficient? These positions are known, then is it sufficient? This appears to be sufficient. Of course, in one sense, this may not be sufficient because at the same distance, if I just see on the upper side, this is towards ground when I am looking, but if I see towards upper side, that is also, there can be another point on the upward side which can be having the same distance. But anyway, if I just say that if we let us look into the ground side, then it is otherwise sufficient. Well, now question is that, and provided these positions are known, this position must be known, position of this bird and this must be known. Now how to measure this distance? How will measure this distance? Say we know, all of us know that sound will be traveling by some speed. Suppose this is creating a sound and then that sound is, sorry, again, say suppose sound has a, travel speed and then travel time. If I know, suppose it is creating a sound, sound is not coming here in this system, otherwise there was a sound also in this PPT. So if the bird is creating a sound and I record the sound here, which is generally we do in many of our present technique or technology, then I can find that if I know the sound and sound into the travel time, that will make me give me this distance. Okay. Then similarly, if I know, similar for this one also, and if I know the travel time of light, say what speed the light is moving, and what is being emitted here and what is coming here, if I get it, then I can get the speed of the light into the time. So that is very common, our velocity into time is equal to the distance, so we can get it. Now in that sense, taking that understanding, if we just move to this one, that is basically distance is equal to speed of the signal into the time to receive the signal. So that is very common thing. Now this signal, the speed of signal can be, as I said, that it can be, suppose this one, our sound or light or any electromagnetic wave. Any electromagnetic wave, that can be the signal. So that way, when we talk about this kind of system, then if we see that why we always talk about, I think by this time you are doing that, all of us doing that, probably, I'm not sure what has gone before that 4 satellites are minimum necessary. Now why these 4 satellites? Because 3 informations are there, X, Y and Z coordinate. And then one, you are having the equations feed into this is equal to distance, so these equations are there, 3 equations. From that we can solve for 3. Now why this 4th is required? That is actually basically we need 4 satellites. Why? Because our horizontal position X, Y coordinate, that is important, and the vertical position Z coordinates is important. So these things we need to know. At the same time, we also need to know one point, receiver clock error. Now what is that receiver clock error? On that I would like to throw some light, considering that some of you may be from different fields, so that way I'm just trying to give these things. Again there, as you see, intentionally here, this is a figure made by someone, I have not made this figure, but then this position of these are kept in a quite in a symmetrical form or in a part apart. Now here, when we measure something, say probably have you done any study on like stereo pair kind of things in satellite data? Stereo pair, that in GIS, that is no, no? Okay. Anyway, now suppose, let me talk in different terms. Say, if I see, suppose here one person and another person on the far distance, how we can understand that this person is closer to me as compared to the person standing at a distance, and how we can do that? Because we have two eyes, and it is actually standing one angle at the object. So if this angle is, if it is close to me, this is wider angle, and if it is far, then it will be a narrower angle. So based on that, we can sense that this object is nearer to us and the other object is at far distance from us. Now, how far we can do this? Suppose the object is at, say, 200 meter away, and another objective is at, say, 210 meter away. This distance is, suppose from here to here only 2 meters, is not it? From here to here it will be around 2-3 meters. Now I can find out the 3 meter difference. I can understand very well. Suppose one object is at 200 meter distance, another object is at 203 meter, behind that object. Will it be possible for me to distinguish which one is closer and which one is away? Will it be possible? This will not be. Why? What is the reason? Why we cannot do this? If this is the principle, mathematically we should be able to do that. Why? Because the angle that is forming, angle that is created there, between 203 and 200, that angle created is very narrow. And the difference between this angle will be very, 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 very less. And that way it becomes extremely difficult to distinguish between these two angles and to find out which one is actually closer, which one is at behind. So that's the problem. But here it is, though difference is same, 3 meter, but here it is quite, angle is there, and here also we have the difference of angle is there. So similarly, this is one point why I am mentioning, because when we do GPS reading, when we take GPS reading, which satellite we are capturing is extremely important. If suppose 4 satellites, if these are very close, then we will not be able to get a very correct reading. Okay. Now with this, let me move to this particular point. I always take this opportunity to explain what is receiver clock error. Means, suppose from here to our inauguration time or whatever we were there, if I carry this clock, then suppose some time is there, and if I move with that clock and if I go there, and if I see that what is the time taken, and if I know my speed, I can always find out how much is the distance, because my speed into how much time I have traveled. Now, let me just put a small arithmetic problem to all of you. Say, I have started from this position, from the position A, I am starting, and I am moving with a speed of, say, 50 meter per minute. I am moving with a speed of 50 meter per minute, and I have reached the position B. But unfortunately, I am not wearing a watch. So, when I have started, my time was, say, 12:37 or 36, say 12:36, and when I reach this point, that clock is different from this clock, okay? And when I have reached this point, then my clock time is 11:44, and I have moved with a speed of, say this, I have moved with a speed of 50 meter per minute. Now, can you just simply calculate how much is the time gap? 8 minutes. Okay, 8 minutes. Then what will be the distance? What will be the distance? 400 meter. Okay. So distance is 400 meters. So that way also we can find it. Now, if I tell you one point, if the clock B is late by 2 minutes, I'm not carrying the clock, so there can be difference between these two clocks. If my clock is late by 2 minutes, not my clock, if the clock at B is late by 2 minutes, with respect to the clock A, what is the distance actually is being calculated, or what will be the actual distance? because the clock is late by 2 minutes here. So that means this time, actual time will be what? It will be actually 11:46. It should have been 11:46, but the clock is late. So if it is 11:46, then actual time taken is 10 minutes. My speed was say 50 meter per minute. So what will be the actual distance? Actual distance will be 500 meter. So we end up in underestimating the distance, or sometimes we may, if it is faster, then if the clock is fast, then we will be overestimating it. So what is not known, the satellite, these are all satellites are in different systems, in different navigation systems, different satellite systems are used. And their clock we may ensure that, okay, their independent clock are in quite synchronized way, but the receiver can be different. Where we are receiving, say, in our GPS or in the GPS or whatever it is, that may be different. So that way, there can be an error. So always in the equation, we'll have to add that error, and then we'll have to calculate that thing. So this error become another unknown. Because of that only, we need 4 satellites, 3 unknown position as well as 1 clock error. So that is unknown. Receiving clock error, again, not the clock of that satellite where we are receiving it. Well, with that, let me move to the next point. I mean, just to summarize what we have talked about so far. So this indicates that we need minimum of, sometimes this doesn't work, we need minimum of 4 satellites whose position are known. Again, the position must be known at the time of measurement. Then, US Defense Department actually launched 24 satellites. That is long back. US Defense Department launched 24 satellites, and that is called actually Napster, Navigation, Satellite and Ranging GPS. That was from 1978 to 94 they were launching, and finally 24 satellites were made. Now it is more. Now number is more. So in such a way that at least 6 satellites remain in view from any point of the Earth's surface at any instant of time. Well, so wherever you are on the Earth, at least 6 will be visible. We need 4. So if we get 6, sometimes this 4 may be very narrow, so we'll take the most wider one and then we'll get the best result. And distance from the satellite to the receiver need to be calculated accurately. That is because distance is very far, and in the previous slide, whether you notice or not, but then I forgot to mention, the time required for the signal to reach the receiver from an overhead satellite. Overhead means just if it is above and directly coming in, that time is just 0.06 second. So it is, time should be very precise. Otherwise, a little bit difference means it will make a quite, huge difference in the error. So that's why we are so concerned about the distance measurement. Okay, that's apart from this Napster system. Distance from the satellite, some other satellite navigation system, that is constellation, we call all the satellite combining. So there are constellation are, say GLONASS, that is actually by Russia, then Galileo by European Union, and Beidou by China. So that way some other satellite system has also come. Now there are discussion, of course, can we utilize all the satellite in together for benefit of mankind to get more and more information so that our accuracy increases. Well, now this is the status here, and then just to show, this is again very popular, video that is available in the net, you can also get it. Now you see the globe is moving, and then from any point, the black point are what is visible from you, and then satellites are moving like this in different orbits, and you see the number is never going below, say 6 or so. It is like not going below 8, so at least all these satellites are visible. All 6 it is going. So at least 6 satellites are remaining visible from any position of the Earth. So that way actually this satellite constellation are moving around, and that's why GPS we call, but then also it is said the global navigation satellite system in general. Because it is not just positioning, now we utilize this for various other purposes also. GPS is, as you know, global positioning system, but that this is generally basically global navigation satellite system, and then this can be used for various other purposes. Okay. Well, now let me just go to the next slide here with this. Now, need of 4 satellites is already established why it is required. So then we actually measure a pseudo rand. These measurements are actually contaminated by several things as we have discussed. One is that satellite and receiver clock synchronization error that has been elaborated. Satellite clock and the receiver clock, there may not be synchronization. Then correction of satellite clock error may be done by applying a satellite clock correction in the navigation message. That means all satellites are moving. Suppose there is a ground control for there, whatever in the space, that clock can be corrected from the controller position. From controlling, you can send this message is generally sent by radio wave. Well, waves are different, and probably many of you know. So through radio wave, these are sent, and this can be corrected. But the receiver clock correction is very difficult. That's why this is treated as additional unknown parameter. Thus the unknown are all these. There is 3 receivers coordinate as well as the clock error. That what is just to summarize what we have discussed so far. Okay. Now, next point is this one. What we call as basically this one, that the satellite coordinate. When we are saying satellite coordinate, when we are saying, these are given in WGS 84 system. Okay, I think many of you have used this thing, WGS 84. Very common, we use these things. It is basically World Geodetic System, and this is nothing but a datum. This is nothing but a datum. We'll have to always, for any survey, we'll have to have a datum, and thus, based on this datum only, we are giving the satellite position. Okay. Now, if satellite positions are given based on this datum, then whatever we are measuring, whatever elevations we are getting on any surface, that will also be based on that particular datum. And that datum is basically WGS 84. And then, of course, different datums are available. I'm just for your information, I'm giving that other systems are like North American datum 83, then GDA 94, ED 50. So there are different datums actually. And then these datums are being used by different organizations. Some local datum are also there. Now, what is the difference between these actual elevation and, okay, like Survey of India use data. In India, what datum we use generally, mean sea level is used. That probably whatever discipline you have followed, but if you have done the basic survey, we all know for various our purpose that mean sea level is considered as the datum. Now, this mean sea level is observed for 30 years or so, and then we fix the data. Now, on the globe, basically on the whole Earth surface, here you can see the blue line is actually showing the sea level, mean sea level we can call, and in different part of the globe, it is actually different. And for India, what is mean sea level we use? Generally, when we study, when in our time when we were student of studying very basics of survey, at that time we were reading in our survey book that mean sea level of Karachi is used. Maybe some of you in some books still it is there. I do not know. It was used. But
Bombay.
Yeah, now it is Bombay High. Now it is Bombay High because earlier it was decided when we were all countries were India, Pakistan all were together. Then it was used for India also. Now it is Bombay High level is considered as the mean sea level. Now that level will be different, and then Survey of India use this one. Survey of India actually, if they are using this one, and then they are providing, say, level at different point. This is very important point. That's why I am bringing this into point, because whatever you are getting by GPS, that will be with a different data, and in some location there can be quite significant difference between these. Google Earth, again they use a different data. So in Google Earth elevation, whatever you will get, and Survey of India, that may not be matching. That will not be matching. Okay. Now different DEMs are also developed by different organizations. So those data always may not be matching. So your elevation may not be matching. So you will have to be careful in deciding, because particularly when my background is basically water resources and I do a lot of hydraulic modeling, river modeling kind of things. Now there, when we do the river modeling, suppose gauge that I am seeing, okay, this is the elevation for this surge, this is the level. Now when I do that, for a particular area, suppose I want to find out how much will be the flood level there. How much will be the flood level that I want to find out. That I will be doing based on the river water, how much it will be coming, return period, and all these things I will consider, and accordingly I will find it out. But those levels are based on Survey of India data. Okay, so wherever it is, so based on that the stations are installed and accordingly it is found out. Now you are trying to understand whether this area will be submerged or not. Now for that, if you use another data, that may be quite erroneous. In fact, it has happened several times. That's why I am telling that people are confused, and then they were trying to decide, because a lot of things need to be decided. Suppose you want to install a solar power system, okay? Solar power. The panel should not be submerged. Now for that, what elevation the panel will have to be, at what angle, what elevation. So now if these are not decided very precisely, then there may be problem. So with this kind of things, basically what is the difference? That this is the sea level shown, and then actually basically geoid means one, this ellipsoid kind of thing, because Earth is not exactly circular, it will be having different, compressed little bit on both sides, so it is like a ellipsoid. So this difference we need to do well. Then this term is distance measurement, how we do that part also I would like to touch very quickly. That basically receiver, I am saying that okay, this can be pointed out, but then say this receiver identify each satellite signal by its transmitted distinct course acquisition code, or another P code is there for military devices. Now there, any signal, now we are very familiar to any barcode like black and white, if you scan you get a price, it's not it, if you scan you are getting something. Okay, so like that, there are a specific combination of say 0101 bit kind of things. So with that combination, each of the satellite is sending this signal, and receiver can generate same signal from its receiver. So for all the satellites it can, for which it is designed, they can emit signal. Now, so that is from that when a signal is coming, at the same time this is also generating a signal. So when this signal will come and it will completely match with this one, this will indicate that this is the time required, and it will be happening several times. So after several times you are very sure that okay, this is the time required when you are getting that signal and this signal is matching. So that way we can find out the time that has required for a signal to reach from this to that. And then speed is known, so from that we can find out the time. And then for precise signal for military purpose, actually we use very large number of bits, and then for general use we use very, slightly lesser bit there. So that way we do it, okay. So now this is very easily, I think we can just show here. Actually distance measuring, this is one of the things, but we have different spectrum, okay, and the microwave is on this part, and radio is on that side. So this kind of wave is coming, suppose, yes, photographer, it is important, everything will go off, finally whatever will remain is the photograph, okay. So yeah, ठीक है मेरा pause. Okay. So this is what, as you can see, that signal is transmitted by the satellite. Suppose this is it is just arbitrarily rough. So this is the signal. Okay. Now this signal is transmitted by the satellite, and this signal is emitted by the receiver. Okay. Now this is moving and it is not. This is moving, it is reaching but not matching. This is moving, this is completely matching. Like that, after some time, it is continuously coming. So after some time you will find that it is matching, and that's the time what is taken for this signal to receive this point. I'm giving it a very raw, in the school level probably it is better to, but then sometimes it is important to grasp the things, so I'm trying to put it like that. The actual signal is quite complicated. So this is how we measure the distance, and then it helps us in understanding the things. So now we can come to that error in GPS and scope of elimination. Okay, there can be several error that can come into our GPS reading kind of things. One is ephemeris, error. That is, this is basically giving the satellite's own precise orbit. We think that satellite is moving in a particular orbit, but this may not be exactly that one. There can be always some deviation of that in simple term. So orbit shifting due to gravitational force basically. So that can introduce some error, because we are thinking that it is coming from that position, considering that this is the orbit. But it may be some deviation, there may be. Then residual satellite clock error. Satellite clock is corrected in all the satellite, but then still there may be some error. Receiver clock is already taken into account, but the satellite clock itself may have some error. So this is also one point. Then multi-path error, as the signal is sent in all direction. So what is that? One can be touching a hillock and then again it is coming, or a building, then it is coming. So there may be several paths is created, and then several signals are being received at different times. So there may be some error, but this particular things is now used advantageously also to understand different other things. I'll just touch on that very briefly. But this is, though it induced error, now for that dual frequency are used and different things are there. So this is one source of error. Then atmospheric error. Actually in ionosphere, when the signal is coming, in ionosphere, because of presence of charged particulate air, so there may be some error coming in. And in troposphere also, there is the refraction of the wave, so there will be also some delay in the speed. So that way, as the we consider that speed is known, so but then speed may not be always exactly what I'm thinking, because or what we are thinking. In ionosphere as well as in troposphere, there may be some delay. That's where we can get some error into this. Satellite geometry, as I told you at the very beginning, that if it is very narrow, then there can be error, but if it is very wide, we can have a better situation. Well, that way even satellite altitude can be slightly changing, so that way there can be some error because of that. And site displacement effect, where you are there, so you are installing your suppose base station somewhere, but there can be some displacement of the receiver, or there can be settlement can be there in the site. In the long run also, there can be in the very large scale also it can be, or in a small situation also when we are doing with a mobile system, there also it can be. So that is another condition. Then selective availability. Sometimes because of security reason, some satellites are not given properly, not given intentionally. So that is again another point. So these are the possibility of some error. And these are of course general range, and now with dual frequency this has come down, but this is a old slide I made, but then this is basically say ionospheric effect can go to 5 meter, shift in the satellite orbit, this can go to 2.5 meter. Similarly, the calculation rounding error, that is also there, calculation rounding error that can go to 1 meter in space basically. So like these are some typical error. Tropospheric effect can take to 0.5 meter, and then multipath effect can go to 1 meter. Actually from different studies these are coming. We have not done any study on that line directly, but then this is what is possible. So we should be careful on that aspect. Now that's why differential GPS is used. Now in differential GPS what? Suppose we know a particular location, and this is of course if we stand there for a long time, if we put our GPS, then, and this is what is say DGPS we call. Whether you have the DGPS in your here in this?
Yes, sir.
You have. Okay. So there, basically what that suppose you know a particular location, its elevation, you are putting it there, you are adjusting that thing, or you are standing it for a long time, it is corrected. Then you will be knowing that what is the error actually coming into it. Now that error and another GPS will be moving that we call as a rover, and then to the roving GPS we can just apply whatever error is there, that correction we can apply to the other roving GPS. So at any point we can correct it. That can sometimes be done on real-time basis, sometimes you can do as post-processing also. So if you have there and if you have the opportunity, then you can probably show that as well. Well, so this is what is being explained here. I mean nothing different from what I have told. So basically on stationary GPS, the calculate the error and it is applied to all. And this accuracy get improved to within 2 meters, or it can be even much better. Now we are talking about dual frequency GPS also. In fact, in your mobile, you will be getting that kind of things, and you are getting that. So that way, actually, what is the frequency? As I showed you, there the microwave level, or there are L1, L2, L3. If you see here, if I just go back to this one, just for those who are very here you see your wavelength are changing here. These are long wavelength kind of things we are getting when we go to the microwave. So these are basically, that's why it is called as the L band, and then low frequency and long wave. So that we call this L1, L2, L5, L3, like different bands are coming. Are frequencies used by GPS satellite to broadcast signal. Okay, and L stands for basically long band, also linked with the low frequency and end of the microwave. Now when two frequency band are utilized, suppose it is not just one signal coming, two frequency, same signal, but then it is two frequency it is coming, then it becomes convenient that we get more information, and there are interior calculations are there. When you have more information, then we can eliminate some of the error and we can make our signal much improved, and that's why accuracy has also improved a lot. So different devices claim that our accuracy is going to now millimeter level, so that way we can have this. Okay, so this can reduce the error caused by the environmental interface. Well, so with this saying so, now I think we can move to some of the application. What is the time now? 15. And how long you can tolerate me? 15 minutes. Okay, good. Fine. So that way, some of the field application, I'll just go quickly so that I do not overshoot the time. Well, now, say field application, I'll start from long back. Now it is 2025. Okay. The system at that time was not that sophisticated. There was a severe erosion in a place called Swalkusi, which is basically it is very famous for silk cloth. Ladies will be more interested in that. So silk cloth, it was famous, and that way it is called as a Manchester of the Northeast kind of things. So this, if you see, there is a location where severe erosion was happening in this part. In this part, there were severe erosion. And then these are left long. I am skipping this part, and this is located between two hillocks. Somehow it doesn't work sometime. So so there are, here it is clear. Now here you can see that this is one hillock, another hillock here. So it is the severe erosion took place, and then from the texture itself, you can understand that it was, a very populated area, and lot of industries were there. Industry means each house was like a cottage industry there preparing this. 34 houses were washed away. 34 houses were washed away. So very severe situation. And one fine morning, I got a call from the local water resource department that Professor Sharma, can you come and help us do something? Because river Brahmaputra is flowing in the reverse direction. It's very, but then when I just heard that point, I know that Brahmaputra cannot flow from, it flow from east to west, so it cannot flow from west to east. No river can flow in the reverse direction. So something must have happened. So we rushed to the point, and then I was, of course, understanding what is happening. Then we analyzed this. Of course, seeing there, going there, I could see that it is a huge whirlpool, and that river is flowing from this side. Actually, it is flowing from this side, from here it is coming from this side and it is coming like this. And generally we know that erosion always happens on the other side of the river. When the current is like this, it will be eroding this part. But erosion has happened here. That is most interesting point. And there was a very large whirlpool like this, and it was rolling like this, and it was causing the erosion in this part. And this distance, the river Brahmaputra is of course quite wide. This is very narrow portion, and that narrow portion is itself is 2 km wide, and the largest can go up to 22 km. So like that, in some places it is quite large. So as I told you, that 200 meter beyond we cannot understand. So they are not seeing what is going there, but they are seeing the near things and where the Brahmaputra is flowing in the opposite direction. Actually it is coming like that, and one large iddi or large whirlpool kind of thing was formed. So then it was very challenging because we need to do model study and we need to provide the solution. Well, so here you can see how many of you are from hydraulics, I do not know, but how many of you are from civil engineering? How many? Oh, all of you are from, most of you are from civil engineering, okay. You know about the spar, there is deflecting spar.
Yes.
If it is inclined downward, then it is attracting spar. It will be attracting the flow. If it is upstream, then it is repelling spar. So now in 1973, this hill outcrop was behaving like a deflecting spar. So water was thrown away, and then this was not, there was not having any problem. Now when it just came to the very recent, means it was in 2000. I'm going back to 2003-4, that study we did in 2003-4. So this hill outcrop, there was some temple was constructed, and because of that some portion of the hillock was actually, rock was taken from there. It was, blasting was done, and then it took a shape. Some boulders fall in this position and it has become an attractive spot. So now because this shape of this has changed, so flow was coming from this side and it was going like this and it was circulating like this, and it has caused a huge erosion in this part, taking all these 34 houses. Now you can see how long it is. This is me actually. Probably you may not be recognizing. Well, so it is me. We had to do the survey, and then how we did. This is the flow meter that we have, but where we are standing there, because you cannot stop anything there, that position. So we took a very boat also sometimes to measure the velocity, how much time a float is taking. Also we had a sensor there put in the bamboo below, so we were taking the velocity. But the location we took by GPS, because we cannot stop the boat. We are moving somewhere, we are anchoring, and we are finding the GPS location. That way we were roaming around in this part to get the exact bathymetry of the river. So that bathymetry when we got, well, that was done in October month, 1 October month, and then I think, yes, finally when we got all these points were found, and then of course from the satellite data again we were finding where the sandbar are. So accordingly we got the elevations, and this way we could make the bathymetry of the river. Bathymetry means how the shape of the river is. And then using that we run our model. I'm not going into detail, but then this model was, when we run the model, then we could see very clearly that how this circular current is flowing. Okay, so then we immediately provided some alternatives, and then of course here I'm not putting those alternatives. Various alternatives were studied, submerged spar, or what we can do, different alternatives we suggested. Some of the alternatives were costly, some were affordable. So that way we suggested, and finally these were implemented. We went by some submergible spar in between some porcupine screen, this kind of screen, and some submergible spar, as you can see here. So this was provided, and then our assessment was correct, and then we could see that a lot of sedimentation has taken. Immediately next year the river went far off, and then whole portion were sedimented, and then this bank is till today. That means now it is almost more than 20 years. And then at that time when after just implementation of this, because project implementing quickly also one problem. So when this could be implemented, so I was called to that people, local people try to give me gamsa and all these things. We have that silk things not there. So I told that don't give me this one now, because Brahmaputra is very tricky. and we are also doing model study. Let us wait and see how it performs. So after, I told that after 10 years you can give me, but 10 years has gone, 20 years has gone, now people have forgotten which was done. So people have not only forgotten that one. Now one fine morning I went there to see whether these things are quite intact or not. Sand has all deposited, but then people have started collecting again sand from that part. By here is the by vehicle, then pull cart, in different way they are collecting. This has become now a sand quarry. People are collecting and some people are earning money from there. So anyway, so I always say that public memory is very short. That's why photo is important. So I'm keeping this photo. Unfortunately, my photo is also, my photo is there. People will not believe it is me, but then it is there. So that way it is one. Then I'll talk about one more example. Well, this is basically Iconos image. Now, of course, our Indian satellites are also producing equally good image, but this we got in 2000. We had 2004, we purchased this from Iconos US satellite. This was costing very high at that point. So for an urban study, that how the urban study of Guwahati area, and here we can see the slip filter and all were there. So anyway, this was used, and then this kind of satellite image was used, and then we had to do for hydrological study, we had to do the land use classification. Now, of course, a lot of sophisticated methods are there, and at that time, we had to move and we collected a lot of GPS points, because ground truthing is important. Ground truthing is always important, though we can do it from satellite, but what it is, so every point, what is the GPS point, it's there, so that I'm just showing few points in our first drive, then second drive also we made. So there we could do all this kind of, which is hilly area, which is plain area, what is the land use in different parts, so that we could do very quickly, otherwise it was not possible. So I'm not showing the results here, but then with this we did a model study, and then finally in a pilot project we have developed this one, and then we developed a method also called ecological management practice, and by that now the sediment coming out from the hill and water coming out from the hill is reducing in those where the project is being implemented, where our suggestions are implemented, and that way flood in those areas has come down. But this needs to be implemented all throughout the same situation, maybe here also in somewhere. So just use of GPS I'm talking about. Then again, this is in 2000, I'm just coming here, this is from in 2030. Actually, we were supposed to find out what will be the actually waterway 2. I mean, in Brahmaputra there are several waterways, national waterways. So where should be the, I mean, station? It is not called station. What is called there? In river where the boat will be actually coming, and it is the port. It is port. Where the port location should be. So it was quite challenging, and among the people also there are a lot of fighting. Some says that it should not be here, some says that it should be here. So we were requested to do that study, and then we were told that don't worry, I mean we have big, this is also a boat. This is also a boat, we have very good quality boat, so you come, no worry, you sit there, people will not be, I mean, attacking you, so there is no worry. So you do the study. So we went there, and then of course I was knowing that in all places the boat may not be moving, because draft is required for the boat to move in a very, and we were to do survey in very shallow area also. So we were moving, and then with the boat, with this boat, which is a very sophisticated one, here we have done the survey with the GPS location, everything is fit into it, but after some time the boat could not move. So to the main channel to the side channel, these are the channels where the boat cannot move. And now of course this image and this is not matching. The channel always keep on changing. So we have to move in this channel, and then again in some of the area by a small boat. So this boat was also kept with us, and with this boat we were moving. Okay. Now you can see here the GPS, there it is. Then again putting all those things there on the boat in the middle of the river, we were also a little bit afraid. But then we do not have a space to sit here, but we have to observe it. So we have to sit. There was a small things on the top, so there we were sitting with another GPS and there, and then we were moving on this. We could collect the things, then we could make the model of this, and then finally we suggested that location, And then we could show these things to the people, negotiated, and then final locations were finalized, and this location is now working fine. So these are some of the practical situation. Then this is where, okay, this is in Mekong River. Actually, I was doing some international project there, and then at that time when I was moving with the Mekong, and then I was doing, this is the toneless shape that you can see, because here also one student is now working at it with toneless shape and this thing. So there the CN. So here when we move, then we could find out what it is. We were also moving in boat there, and we can find out with the GPS the location, and the map is in your hand. GPS map is in your hand, so you can have the advantages. This is of course very known things to all of you. And finally the things were improving, and we also got the opportunity to move in helicopter to do some study. So people had developed their confidence, and with that confidence now they spend that, okay, rather than doing a survey, you can do the survey with GPS. This is for a dam, okay, this is for a dam, debunk dam, and in that debunk dam, actually we had to do dam break analysis. How many of you are aware of that? If the dam fails, then water may be rushing at a very high speed causing velocity. So those things we have to do. Now, who are the people who will get affected? So we need to know the where is the people location, where is the dwelling area. So we had to make a helicopter survey there. But at that time, with the helicopter we were moving, and then we were, and I was with all my full family. If anything goes wrong, then we are all happy. I mean, so because the helicopter was flipping like this, there was a very serious issue. Somehow I survived. So anyway, so there we got all the data, and then finally to show you, not showing in detail, that dam break inundation map we could prepare. Time is running, but it is. This you can see that we have made the model finally, and then these are the locations we could record it. We made a low height flow, flying, and we could locate what it is, and with this we could see that which area will be submerged. Actually, we didn't say this much second, only 300 seconds if the dam failed. In 300 seconds it is covering this much. In 1000 seconds it is covering this much. And in 2300 seconds it is going to the Brahmaputra. This is a Dhanbad tributary, this is one. So that way, which are the things which are in very precarious situation and which are in safe position, that we could identify. Accordingly, this work could be processed. Well, now let me come to another things, which is the last point. Well, see, in because sediment transport you are working many a time, and then now we are. This is the latest. I have come from 2004, and then about this GPS application. Now it is 25. So this is now going on one study that we are developing. Now we have a mathematical model also. We have our own model that we call as a Brahma, Braided River 8 hydromorphological analyzer. So with that model, we were trying to understand how is the sediment transport in the river, hilly river like Dibang and Siang, they are in Brahmaputra tributary. So there are so many formulas for different situations like gravel bed, sandy bed, and then for boulder bed, very limited number of formulas, and how it will work, that is very not known. So what we did, we had to do the testing. Now survey is going on. Today also this survey is going on. Initially we applied model with different formula, and we are finding that different formula gives different result. So now how to confirm which formula will be giving best result for a particular type of river. So there we are conducting that survey. This is the base station is being fixed there, of course, and then rover is moving. Then in the river we are moving the boat, and then this is again we are carrying this one, and of course we are using drone also there for survey. So it's combining all these things. This is one of our ongoing project where without DGPS it was not possible to do the study that quickly. So now we cannot think about our any survey or any water resources project without use of this GPS and DGPS. Okay, and now as I told that there are this is again another project that we have deflected or reflected things. So reflectometry is now becoming one very advanced position of science, that if we get the signal directly in one point and then from the reflected from the moisture we are getting or from the ground we are getting, and that way we can use canopy cover. Also, this is a collaborative project with Japan we are doing, where we can measure that what is the NDVI from this kind of signals and what is the canopy cover and what is the crop health that can be monitored. Two systems are there that I am not going in detail. So because my time is over, I think you have, I think, tolerated me a lot. So that way now. So, but then I always do not forget to acknowledge whatever projects I have just shown you, everywhere, actually contribution of my research scholar, all these are my PhD student, and then some are still continuing, and some project stuffs are there, even your Bandita will be here somewhere, there is the Bandita Burman, so that way several of my students are working, and also collaboration with different institutes, and I'll be happy that if I can collaborate with IIT Dhanbad. So this is what is the my system that I always try to work with. And then when I'm coming here, definitely it is important to visit your Top Chanchi in Jharkhand, and I visited there. See, with GPS now I can say that where I am sitting, anyone can say. So that's the beauty of GPS. But always I say that GPS and remote sensing all are very colorful. Okay, you always see any data, it will be so colorful. So we should be slightly careful also, because it can always be some erroneous. I have already shown you what are the scope of error. So to conclude, GPS and remote sensing, with these two, life is changing, so colorful, so wonderful, but be careful, it can make you fool. GPS and remote sensing. Thank you very much. Thank you all.